Welcome to our 6th lesson on electric circuits. Our discussion today will be on power. Now our power has got a symbol of a capital letter P. Note that it must be a capital letter because a small letter would stand for pressure. And the unit in which we'll be measuring power is watt. So W-A-T-T. Another unit in which we can also measure power is joules divided by seconds. And this comes specifically from our older formula which we've already done in grade 8 and 9 that talked about power as the rate at which work is done. Now work was measured in joules and time was measured in seconds, so that's how we got from joules per second to being power, which is also known as watt. Now within my electric circuit, one of the common formulas that you'll come across for power is where your average power is equal to the potential difference times the current. Now this formula can also be broken down in a few different ones, seeing that we can go and replace potential difference with another formula as well as current. Now let's go and take a look at how much different this formula can be. So one of my scenarios is if I have to go and replace current, and we do know that current is equal to potential difference divided by resistance, then I can just go and replace my current as it would have been in my formula with my potential difference divided by resistance. Now this would lead to your potential difference being squared at the top divided by resistance. And this is then your second formula for power, is where I've got potential difference squared divided by the resistance. Now let's go and keep your current the same. So we assume that you still have your current, but now you do not have potential difference. Potential difference can be replaced by I times R. That means I can go and replace my potential difference in my power formula by adding in current times resistance. Now this would simplify my formula to be current squared times the resistance. And this is then the third type of formula that I can come across for power. Now let's go and make use of our newfound formulas and see how can they be applied within a series or a parallel circuit. Now our example that we'll be taking a look at says that we're going to have two circuits. One of the light bulbs R and S will be connected in parallel to a battery with a negligible internal resistance. Now later on when you get to grade 12 you'll learn what internal resistance mean, and that just got to do with the resistance within the battery. But for now you can ignore all of that. You're just going to be making use of your resistance, current and potential difference as you've learned up till now. Now here's my circuit. You would note that we've got a 50 watt bulb and an 80 watt bulb, and they are connected in parallel to each other. Let's then now go and see what does the question ask. They tell us that our bulbs are marked 50 watt and 80 watt respectively. Your bulb S though, and that's now the one that you'll see with the 80 watt, glows brighter than the 50 watt. They want us to go and determine how does this resistance of bulb S compare to that of bulb R, and we need to make use of an appropriate equation to explain our answer. So the third type of variable that we'll be taking a look at, apart from the power and the potential difference that we know will be the same, is the resistance of these bulbs. Now a formula with power, potential difference and resistance is then where our power is equal to potential difference squared divided by the resistance. Now what you would note from this, I need to go and compare R with S. But in both R and S, my potential difference will be exactly the same value. So my potential difference thus stays constant between R and S. And I'm going to end up with a new form of a relationship between the power and the resistance. Seeing that our V stays constant, I'm going to replace it with a 1, and that means that my power is inversely proportional to my resistance. Now in this case, I would have noted that the one with the highest power rating, which is bulb S, was the one that glowed the brightest compared to number R. But we would note though that my power was the highest, but according to my relationship, it meant then that S would have the lowest resistance. So because of my low resistance, remember now the current is going to split up. More of the current will then be running through the S branch than through the R branch. Because the resistance is lower, more of it's going to run through it. Whereas in my R branch, there's a little bit higher resistance, so less current will be running through that, and that's how come, due to the less current, our bulb doesn't glow as bright. So to quickly recap, because my potential difference is the same for both R and S, our relationship is power is inversely proportional to my resistance, and that means that bulb S with the highest power rating of 80 watt in this case will then have a low resistance compared to bulb R that has a 50 watt power rating, and that means that it will then have more resistance. And lower resistance means more current will be running through the branch, therefore you'll have a brighter bulb in this case burning, whereas in R's case, there's going to be a high resistance, thus less current, and a dimmer type of light from your bulb. Let's now go on to the next part of the question. It tells us that the bulbs are now connected in series, but to the same power supply as before. Bulb R now glows brighter than bulb S. So first off, just like in the case when we taken a look at the parallel combination, we need to go and find something that is unique about our series circuit. And our series circuit has got, in this case, the current the same everywhere in the circuit. So that means to us, the current running through R will be equal to the current that's going to be running through S. And that will be the total current of the circuit. Now we've got our power rating, and we have also just taken a look at our resistance. So we need to go and combine these three in a formula which we can go and determine to try to explain why would R then glow brighter. Now, we do know from our previous formulas that power is equal to our current squared times the resistance. So because my current stays the same among my bulbs R and S, we get to the relationship of power being directly proportional to the resistance. That means to us the brightest bulb will be the one with the highest resistance. And we have already established which one of the bulbs had the higher resistance. Let's quickly go and take a look again. According to our previous questions, we've established that our bulb S had the lower resistance, but bulb R had the higher resistance. Thus, because my bulb R had a higher resistance, therefore it will now glow brighter. My bulb H, which we've figured has got a lower resistance, will then in this case also glow less brightly because of its low resistance. So to recap, we figured out the relationship between power and resistance is directly proportional because the current between them is the same, and that would mean that bulb R that we figured out before has got a higher resistance would thus then have a higher power output, seeing that it's a directly proportional relationship, and therefore it's going to be the one that's going to glow brighter.